Hello everyone. With the continuation of the part 1 of this lecture, here we will be deriving the expression of inductance, per unit length inductance for two-wire transmission line. Okay. So before going to discuss this, derive this expression, so we know the internal flux linkages, how it is happening due to the internal magnetic field intensity. External flux linkages happening due to the external magnetic field intensity. For this is the internal magnetic field intensity, for this is external magnetic field intensity. As we know, this internal magnetic field intensity means what? I rho 2 pi r square. Here it is I 2 pi rho. But we have to, what we have to do? The partly we will be doing the calculation. Okay. Before going to do derive this, one more thing I want to discuss. This is what we are considering, just notation I am giving. So here one conductor I have taken, here one conductor, one wire, one another wire. So the radius of this wire and this wire are same, and if this wire is considered as a go wire and this is as a return. It's a current carrying in this direction and it is in this direction. Okay. So if the transmission line is placed in what? In free space. So here in the relative permeability would be 1. Okay. And we will be discussing only with this. Okay. So the relationship between the magnetic flux density with the magnetic field intensity is this for this case. Okay. So now what would be the flux linkage for a small change of area? For a small change of area, how it is? Suppose inside this I am considering one small rho radius, but with the change of rho. Suppose the small change of d rho. Suppose if you change d rho, then what would be the magnetic flux? Magnetic flux, what we know? The flux is change of flux. Small change of flux means what? The magnetic field intensity into ds. So magnetic field intensity in the direction of what? Phi. We know this was H was what? And the I rho 2 pi r square and a phi. And so the area, what would be the area? So area would be in the direction of rho d rho d phi in the direction of d rho dz in the direction of phi. That direction, area, this area in the same direction and the flux, magnetic flux density in the same direction. How much flux is there? That means with this area, how much flux is crossing this flux? How much flux is crossing with this in this area? Suppose here to here, how much flux is crossing this flux? So this ds we can consider as a d rho into z, if we consider z as a length of the conductor, so d rho into L. So suppose if you consider the per unit length, per unit length. So per unit length, it would be the d rho only. So now the d phi would be d into d rho, okay, into 1 for. So now the flux linkage, what we know the flux linkage is? So firstly we know flux linkages. Flux linkages, we know that the number of turns and the what? Flux d phi, number of turns into flux. So here what would be the number of turns? So for the conductor, as we know that this is rho is less than r. If rho is less than r, okay, the turns will be the pi r square divided by pi, sorry, this is not r, rho square by this. It would be the number of turns. Okay. As we know the B, the magnetic flux density, mu naught, H means what? I, rho, 2 pi, r cube, and this is in terms of, in the direction of Fi. So what would be the total internal flux linkage? Total internal flux linkage is, what would be the total internal flux linkages? It is term present as a lambda. So this is a rho equal to 0 to capital R, and B is presenting here so it is I mu naught rho 2 pi r square, and here it was d rho, and one more time turns, for the turns this term is coming. Okay, so this is the expression. Now here we will be getting I mu naught 2 pi r to the power 4, that expression rho equal to 0 to r, and here the rho cube into d rho. If you get the integration of this, so finally you will get the mu naught I into 8 pi. So this is the internal flux linkages. This is the expression of internal flux linkages. So it is clear that the internal flux linkages doesn't depend on the size of the conductor, means it is not depending on the radius of the conductor. Radius of the conductor, yeah, r. It is not depending on that r. Okay. So internal flux linkages are not depending on the this r, the radius of the conductor. Okay. So it was due to the internal flux, internal magnetic flux intensity. What would be the internal flux linkages? Now for the second case, the external flux. external flux linkages. What would be the external flux linkages? As you know, the magnetic field intensity for that 2 pi rho A phi when the rho is greater than R. Okay, as you know, the medium rho R is I, because it is the air medium we have considered free space. Now, the number of turns in enclosed here for this, here also the magnetic field intensity, flux linkages we have to find. Flux linkages, number of turns into the number of turns into the flux, small change of flux. So what would be the, because here number of turns would be C. It is behaving like this, na? It is behaving like this, and we have considered this the center to center distance of the conductor. Center to center distance of this conductor, the distance is capital D. Okay, from the outer surface of the conductor to the center distance is D. Okay, so due to this presence of two conductor, what would be the internal external flux linkages we are going to find. So due to from this rho is what? So here for these flux linkages, the outer flux. So outer flux only the conductor one time is linking. Na? So the number of turns for this case would be the 1. And the magnetic flux per unit length. Per unit length, what would be the magnetic flux per unit length? Magnetic flux per unit length would be the d phi. B means what? Mu naught I 2 pi rho and d rho. This would be the magnetic flux linkage. Okay, so and the direction and the total flux linkages and the total flux linkages. So total flux rho would be the R to D minus R. D is the center to center distance of the two conductors. Okay, and I omega the mu naught 2 pi rho. Okay, and this is the d rho. So from this what will be getting? So you will be getting like this one equation, 2 pi mu 0 I 2 pi ln d minus r by r. Suppose in the case of this, suppose here to here, so if r is the spacing between two conductor D, spacing between two conductor D is much more greater than R. If it is happen, then what? So it would be the expression is simplified with ln d by r. Okay, is simplified with this. Okay, clear? So now the total linkage of this flux linkage So total linkage, flux linkage due to the external flux, what we know that this mu naught I into 8 pi and plus the mu naught I 2 pi ln d by r. Clear? So if we take common as the mu naught I and pi 2 pi, so what 1 by 4 will be there plus ln d by r. Okay, so the total flux due to the this flux linkage is for one conductor. This flux linkage is for one conductor. Okay, so the total flux due to both conductor, total flux is due to both conductors, the 2 times of one conductor linkage, 2 times of one conductor linkage. Now the inductance per unit length. So inductance per unit length. So the inductance per unit length is the flux linkages, total flux linkages divided by the current. Okay, so what we will be getting? This expression is 2 into mu 0 1 8 pi plus mu 0 I 2 pi ln d by r, capital R. This was the expression for the flux linkage, per unit flux linkages, this for the current. So finally from this equation you will get the final equation as if we put 0 as a 4 pi into 10 to the power minus 7, 10 to the power minus 7, as you know that then the L would be the 4 into 10 to the power minus 7, 4 into 10 to the power minus 7 ln d by r into 2 to the power minus 2. So this expression we will be getting. Okay, for the both conductor. Okay, the flux linkages. So this is the expression of the inductance, total inductance for a two-wire transmission line. Total inductance two-wire transmission line. That means two-wire transmission line. That means one single phase transmission. So for this, if this is current carrying conductor I and this will be the minus I, and if it is spacing between P and the radius of this conductor is R, so if the conductor is current carrying conductor if it's carrying I current. So the flux linkage, the inductance due to this whole transmission line, to this transmission line, working transmission line, the inductance will be the 4 into 10 to the power minus 7 ln d r into e to the power minus 1 by 4. This would be the what? The inductance Henry per meter, because we have calculated this as the what? Per unit length inductance. Where we have taken the per unit length, the flux, the change of flux, this small flux, there we have taken the line as a what? L as a 1. Okay. So this much things what we have. So far what we have discussed, we have discussed about the some key elements, two-wire transmission line or a single phase transmission line. Okay. What is the internal magnetic field intensity? What is the external magnetic field intensity? For those, what are the magnetic flux linkages? And remember one thing, so for the internal magnetic field flux intensity, the trans is nothing but the pi r square, this pi rho square by pi r square. So this is the trans, number of trans for the external, but for the internal only one trans is there. Okay, because the external flux is linking one time the conductor. Okay, but internal flux, what? Internal flux is what? Suppose this is the cross section, na? Like this. So from there to there it is R. So we can consider as a turns these things. Okay. So the turns is for the single phase transformer, means for internal flux. So we are considering pi rho square by pi r square for internal flux. Okay. But the external flux, the flux line is linking one time conductor. Okay. So these things. So hope I think you have understood this topic. Ask on the comment box. Okay. If you do useful this lecture, so please subscribe the channel. And if somebody is there need this type of lectures, so please share. Thank you all. God bless you.